Hello everyone, welcome back. So, we have been discussing about how to use the discretization of different derivatives to solve some model equations. For example, we started with the linear convection equations, and what we basically noticed is basically if you use, for example, the first derivative in time, the forward derivative in time and backward in space, and we are able to solve it. And what we noted is that it is stable for lambda, basically lambda, which is defined as a CFL number, okay, which is basically C delta t by del x, and it was stable for lambda less than 1, right. So, that is what we noted in the last class, right. Uh, we also looked at that these schemes uh, are stable only when we use the appending scheme. So, solutions are stable only with the appending scheme. When we tried using the central differencing, it did not work out, right. So, yeah, this is what we saw basically that when we use upwinding, basically it respects the flow direction, the characteristic, the direction of the information flow, and that is why it works the upwinding, but the central differencing does not work in the convection cases, right, basically the hyperbolic cases. And the lambda, which was basically given by C delta t by del x, it was stable for less than 1, that is what we saw in the last class, right. And what it actually mean is that so if C is the convection speed and delta t is the time step, right. So, the distance it will travel in one time step will be C delta t, and the grid size is delta x. So, when I say the C delta t should be less than delta x, that means C delta t by del x should be less than 1. That means that whatever information that goes from one grid point to another grid point, okay. So, the C delta t or the delta C t should be in such a way that it should not jump over the cells, right. Suppose C delta t is greater than delta x, then it will jump over the cell and it will lose the information there, and these kind of basically solutions become unstable, right. So, this is about the CFL number, and we looked at the linear convection system. What if the system or the equation is nonlinear, then what happens? So, earlier we had seen that nonlinearity can lead to shocks and all. So, let us look at from the nonlinear convection point of view. So, now I am replacing this C with U here, okay, because it is nonlinear convection. So, now the convection speed is same as the variable, the dependent variable, right. So, now you are using FD in time, the forward differencing in time, and backward differencing like we did earlier. The only thing will be here, instead of C, the constant speed, you have UIN, right, and you can go back and solve it. So, left hand side is in terms of n plus 1, and this is entire in terms of n. So, you know the solution at n, and you can time march and get the solution at n plus 1, like you did for the linear convection. So, once you do that, so this is what will happen. So, this is an example I have taken where the basically grid size is very coarse, and it is a 0 for less than 0.5 and 1 after 0.5, 0 after 1, and between 0.5 to 1 the value is 2, right. So, once again let us say this is u and this is x, right. So, x, so my x is between 0 to 2, and between less than 0.5 and x is less than 0.5 or x is greater than 1, your u is equal to 1, else u is equal to 2, right. So, this is just to show you that how things change. So, you can see that now u is smaller here and u is bigger here, right. So, bigger is traveling at a faster speed and small is traveling at a slower speed, right. So, you can see that as it goes, so if you start with a square wave and then the top one is moving faster, so it will go fast here, and this one moving slower, this will go slow, and this will go like this, okay, and come back like this, and it will become more and more steeper. So, this is what will happen, it will become more and more steeper, it will go like this and it will come back like this, okay. This is what is happening here. Now, you can see there is some diffusion here, this should not happen. This is because we are using a very coarse mesh. If you use a proper mesh, the diffusion will not be that much. There will be some diffusion which we will see in the later classes, but it will not be that much. So, eventually the idea is to use a kind of mesh which gives you the least diffusion and at the same time it is stable, right. Here also you have to maintain that the lambda should be less than 1, although that the stability criterion lambda should be less than 1 is derived for the linear case. We will see that using the von Neumann stability analysis, the theoretical approach, but it works for the nonlinear cases also mostly. In fact, it is more restrictive in the nonlinear case, right. So, if you look at the old example that we had there, right. So, this is the example that we have been looking at. So, this domain is from -1 to 1 and between 0.5 to -1.5 to 0.5 the value is 1, otherwise it is 0. The same thing what will happen. So, this is the little code here, the only difference that you have here is instead of C you have ui, right. So, now the speed is 0 here, right, and speed is 1 here. So, this is maximum speed and in between the value is changing from 0 to 1. So, once you go on the later time step, so if you look at go to t equal to 0.2 second, right. So, this has moved up to this distance, okay, whatever u delta t. So, this is u is equal to 1 u delta t, but this is moved 0, right, and accordingly depending on u it has moved at different locations. And so, your profile will be, it will go like this, okay, and like this, right, and you keep on doing like this, okay, and eventually what will happen is that if you keep on doing like this, it will basically make a shock here, okay. It cannot cross this line, so it will make a shock here because the value is 0 here as well, right. So, it will have basically the steepening and there will be shock here, right. So, this is how the shocks are formed, we have seen that earlier. And this is another example. So, let us say this is your initial profile and this is a kind of sine wave, okay, and I have added 1 into that 1 plus 0.5 sin pi x. So, this is the initial profile and you can see that it is now very nice. The blue line if you see, there is like a sine wave, okay, basically increased by amount 1, okay, but as you keep on going for next times, you can see that this if you look at this at the final time of t equal to 0.6, it goes like this. So, this is now becoming more and more like an expansion of time type, and if you look at here, it becomes more and more like shock, and if you keep on going like this, it will basically eventually become like this, okay, something like this. So, this is called the steepening. This is the nonlinear steepening which is happening because we have the waves traveling at an initial profile which is different at different locations, right. So, this is another example of nonlinear steepening. Now, so we looked at the convection, let us look at the diffusion equation. So, that we are not considering. So, we are what we will be doing, we will take convection first, okay, then we will go to diffusion, okay, and then we will mix the convection. So, they will have convection diffusion, okay. If we are slowly increasing the complexity level, then it will be first linear and then non-linear, okay, and then finally, we will solve basically the multi equations, and you can also do maybe I mean 2D and 3D, basically increase the dimension also, but that we will cover later, right. So, the reason is we want to look at the property of the schemes separately for the convection, for the diffusion, and when we combine both of them, right. So, now again we are taking this 1D diffusion equation, right, and we are using the central differencing for this delta u by del x square, it is an even derivative. So, this is the central differencing formula for that, right, and then this will be u I n minus 1 minus u I n by delta t. So, if you rearrange it, it will become like this, right. So, finally, what just like we had this convection CFL number which was C delta t by del x, okay, we will define another number which is nu delta t by del x square and we call that as lambda d, okay. So, this we will name as the diffusive CFL or diffusion CFL, right. So, again you have everything in terms of n here and n plus 1 here, and the parameter that you have is the diffusion CFL number, which relates again the delta t to delta x, right. Now, you can note one thing. So, we earlier we are comparing the C delta t to delta x, right, how much it has basically propagated in delta t compared to what is the spacing between the grid. Here, because the diffusion, if you recall, we have discussed it earlier. So, this is like an elliptic process. In fact, it is in this case, because of the time also it is parabolic. So, it is parabolic in time and elliptic in space, right. So, this part is elliptic in nature, right. I mean elliptic uh, equation do, okay, elliptic PD do, that let us say if you have something, you put up something here, let us say you add heat here or something like that, it will basically go in every direction. Okay. So, this is the nature of the elliptic PDE. On the other hand, like hyperbolic, we have to, it will go in the characteristic direction. Let us say this is the characteristic direction, then it will go like this, it will not go in every direction, right. So, this is hyperbolic, it will travel in the direction of characteristic, okay, with the wave speed, right. So, because it is elliptic, so instead of talking about the linear distance that you have in hyperbolic system, we will talk about the area here, because it can diffuse in every side, right. So, the delta x square is a kind of area that you can think of. So, delta x is the grid size, right, and nu delta t, what is the unit of nu here? So, if you think of u as meter per second and t as second, then the unit of nu will be meter square per second. You can think of it as a kinematic viscosity, right. You can so, this if you write, this is meter per second per second. So, this is meter per second square on the left hand side, right hand side this is meter square per second into u is meter per second, and this is below is meter square, this x square. So, this meter square will cancel out, this is meter per second square. So, both sides are dimensionally equivalent, right. So, now nu is meter square per second. So, when you say nu delta t, that means how much is being diffused in this time delta t. So, the unit of nu delta t will be meter square. So, how much area it is being diffused in time delta t, right, and what is delta x square? So, it is like an area which basically if you select the stencil size as delta x, right. So, the spacing between the two grid points, then delta x square is an equivalent area. So, again what we have to satisfy is that nu delta t should be less than delta x square. Just like we had this C delta t is less than delta x in the case of convection problem, you have to satisfy the nu delta t by is should be less than delta x square. How much small, that we will see. Okay. So, here I have taken this uh, lambda equal to 0.4, again the same problem like we had I think this is -1 to -1 to 1, okay, and n x equal to 400 that we had discussed earlier, and the nu I have taken is a new parameter here, this is 0.01, and then what is the delta t? So, the n x will give you the delta x, right, delta x will be basically distance is 2 by 400 minus 1, n x minus 1, that will give you delta x. Now, from delta x and lambda t you can calculate the delta t, right, that will give you the time step, right, because this lambda t is equal to nu delta t by del x square. You know the value of delta x, from this you know the value of nu, you can calculate the value of delta t. Now, we are taking this as a parameter because this is what which will govern the system, whether it will be stable or not. The first thing you want to note that this is nu equal to 0.01, very less diffusivity, and you can see that there is no convection in this case, because this is only purely diffusion problem, and this is being basically diffused, basically the amplitude is going down, right. You can see that this is with time that t equal to 0.2, 0.4 and 0.6, there is a diffusion on these sides. So, whatever things, the sharp corners are now becoming more and more smooth, okay. And if you increase the let us say the viscosity, okay, it will basically diffuse faster, right. So, this you can see that now it is going down also very fast, because I have increased the viscosity 10 times, right. So, it is nu 0.01, this is nu equal to 0.1, and that is why the diffusion is faster. So, higher the viscosity, faster it will diffuse, correct. Now, what we will do, we will increase this to this is I have not mentioned it. So, this is actually lambda d equal to 0.5, okay, and nu is equal to 0.1, high diffusivity case. And you can see that these wiggles are started forming. If you can note it, that when as soon as it reached 0.5, you can see these wiggles starts forming, right. And let us say that you increase this value to little bit. So, this is if you go to 0.501, okay, this is what will happen here. Okay. So, now it has like we saw in the convection case, it is basically the blown up, right. It is not able to sustain the high delta T, and then it is not giving you the correct solution, right. So, what we noted that this scheme we are using FTCS and we are using central differencing because it is a diffusion problem, okay. But even with the central diffusion and the diffusion problem, it is stable for only lambda d less than 0.5, okay. If you increase it even slightly, it will blow up. Now, if the diffusion is very high, it may go slightly up, but theoretically speaking, the limit is lambda d is less than 0.5. Okay. So, sometimes you may have this wiggle kind of behavior sustaining even slightly greater than 0.5, but ultimately it will not give you correct solution if the value is greater than 0.5. Now, how does this 0.5 number comes? So, we had lambda less than 1, okay, for explicit scheme. That means, when I say explicit, I am saying that all the we are solving this u n plus 1 for u n, okay, for the previous condition, and when you are trying to calculate the put the right hand side where the gradient is there, we only put in terms of u n. Okay. So, those kind of schemes are called the explicit schemes, right. For example, if you go to this problem here, yeah. So, everything here on the right hand side, this delta u by del x square is written in terms of n, nothing is n plus 1. So, these kind of schemes are called the explicit scheme. You can also express it in terms of n plus 1, but you do not know the value at n plus 1, but you are still expressing it in terms of n plus 1, and then you can rearrange it. You can put n minus 1 on the left side, n plus 1 on the left side and on the right hand side, and then you what you will get is a matrix system of equations, basically A x equal to b, and you can solve for x. So, that is called implicit schemes, because you have to solve this implicitly, right. Right now, you do not have to solve or invert any matrix here, correct. Now, one last thing you can do is basically add a negative diffusion. Okay. This is a slightly different case where we are doing from minus from 1 to 2, and you can see that when you use the negative diffusion, it basically explodes, right. So, as soon as you have anything where the diffusion is negative, that means the viscosity is negative, okay, it explodes. So, that the nature does not allow such kind of problem, right. So, that is why it explodes, and that is what we see in the numerical scheme also, that the viscosity has to be positive, correct. I mean, it is, you can relate it to the laws of thermodynamics like we studied earlier. So, when you are saying that viscosity is positive, that means we are talking about that energy is either diffused or basically distributed or basically dissipated, right. If you have, it can dissipate as heat or other things, right. But when you say negative diffusion, that means we are kind of adding energy. We are saying that it can go bigger than the system that he had, the energy that it had earlier, and that is why the nature does not allow that, and that is what we see here also. Okay. In fact, we will see when we talk about the modified system of equations, and we will see that as soon as you have this negative diffusion, it does not work out, even if in the leading error, right. So, now you have this we have talked about convection and the diffusion. Now, combine both of them, this is convection, this is diffusion, right. So, just like we did earlier, we will use the forward differencing for the time and backward differencing for convection, because C is greater than 0, and central differencing for the diffusion, because it is a diffusion problem. It basically, if nu is greater than 0, it stabilizes the system eventually. So, we will use the central differencing here, and once you do that, so you can write it down as u I. So, let me write it here, I mean just one step. this is u I n plus 1 minus u I n by delta t, that will be the first part, plus c u I n minus u I minus 1 n by delta x. So, everything will be in terms of n and will be equal to nu, this is u I plus 1 n minus 2 u I n plus u I minus 1 n by delta x square, right. So, this will be the equation. Now, what you do, you put all the n minus 1 on the left hand side and on the n on the right hand side, and this is how it will look like. Okay. Now, you have two numbers here, this is lambda and this is lambda d, right, and you have to see which one, I mean you can calculate the delta t from both of them in a practical problem. You can specify the lambda and lambda d, calculate delta t from both of them and see which delta t is smaller. Okay, I mean which is the smaller one, delta t smaller, and use that delta t for the solution of the problem. If you do not do that, let us say you have used a higher value than let us say lambda d or lambda, it will blow up like we saw earlier. Right. So, this is the convection diffusion problem, right. So, the diffusion is very less, but you can see that these corners are now becoming smeared out here, okay, because of the diffusion, and it is also convecting on the right hand side, right. This is a linear convection. So, there is no steepening or anything here, right, and we have used the value lambda which is less than 1 and lambda d which is less than 0.5. Okay. And eventually, we compare the delta t from both of them and take the minimum of the delta t, calculated both. Okay. And if you have basically higher diffusion, okay, and this is how it will start going in the right hand side, right. So, this is the linear convection diffusion using the FTBS and the FTCS for the diffusion, central diffusion scheme, right. So, this is purely because we are using a higher value of nu. So, diffuse is much faster, right, and it is propagating at the same speed as earlier, which is say equal to 0.5. Now, we looked at the linear convection diffusion. Now, let us look at the non-linear convection diffusion. So, the only change we have is now instead of C you have U. So, accordingly you will have U I n here, okay, and now your the new definition of the CFL number will be basically you have to calculate this U I n delta t by del x at every cell and find out. So, this is your new CFL number. Okay. So, when you write a code, basically you have to see what is the value of u in every time step in every cell, and you can basically specify that no matter what is the value of u, in none of the cells this value should be greater than 0.5. So, it has to be less greater than 1, it has to be less than 1. So, that is how we put the criterion, right. And so, this is what I do here. Okay. So, you can see that I have fixed the CFL 0.8, CFL d as 0.4, okay, and then I calculate this convective time step dt underscore conv. So, this is basically so lambda equal to C delta t by del x. Now, C is given here, okay, I think it should be specified somewhere. Okay, this is u delta t by del x. So, you have calculated the u max, right, which will give you the lambda max, right. So, the delta t, if you want the minimum delta t, so you have to have basically lambda delta x by u max, right, and this number I have given, I have compared the u max and 1 e minus 8 and took the maximum of that just to avoid any 0 value. Let us say your u max is very small value, it will blow up, right, let us say it is around 0, it will blow up. So, we give a very small epsilon value here, so that it does not blow up, the delta does not become infinity or something like that, right, and you can calculate using the diffusive thing also, take the minimum of these things, okay, that is your dt, and then you have this is a convection term, okay, which is using this FTBS u I minus u I minus 1, this is the diffusion term. So, this is FTBS, okay, this is basically the central diffusing, okay, you add both of them and this u I term, and this is you get a nu I, and then you apply the boundary conditions, this is 0 and 0 on both the sides, okay, and then you just march it. Okay. So, this is a loop that we have been doing. Okay. So, you can see that now you have this steepening on the right hand side. So, because of the diffusion it is not basically fixed here. So, it diffuses on both the sides and it goes on the right hand side also because of the convection speed, but ultimately because of this non-linearity it becomes more and more straightened up. So, if you go to further time it will become like this, and this is the kind of steepening that I am talking about. Okay. If you go to further time you will have a shock kind of behavior here, right. So, this is how you can solve the non-linear convection diffusion equation, right. So, now the question that comes is that can we increase the stability limit? Now, this is very restrictive, that the lambda should be less than 1 or lambda d should be less than 0.5, right. So, this is very restrictive, that means your C delta t by del x is less than 1, that means your delta t should be less than C delta x, right. So, if your wave speed is let us say 0.1, so 0.1 of delta x is the maximum that you can use, and if it is non-linear then basically delta t is u max delta x. Okay. So, we had used the, so last time we had calculated, we have given the lambda, and from that we had calculated this, if you look at it here earlier, right. So, you have taken this u max, right. So, when you try to calculate lambda delta x by u max, so that is how we calculated. So, that will work here also. So, the question is, can we increase stability limit? That means, suppose there are problems where we are only interested in the steady state limit. That means, there are many problems in fluid dynamics which can go through an evolution process, but ultimately it will basically become stationary, or it will become steady state, with the time it will not change, right. So, in those cases we are not interested in how it is evolving, right. What we are interested in is basically how it reaches to the final time step, right. So, in those kind of problems, especially there is a problem, I mean one kind of modeling which is called the Rance modeling, Reynolds average Navier-Stokes, where we are interested in some averaging behavior and we want to reach the steady state faster, the d by dt term should go to 0 faster, right. In that case, if we can if there is a approach that can allow us to take higher delta t, if we can get the convergence faster, right. So, that is what we will see in the next class, that can we have an approach where we can increase the limit of this delta t, maybe it can allow us a higher delta t without blowing up. So, we will see those things in the next class. Thank you very much.